In this unit, we're going to learn how to create an image interpretation project in Collectors Online. But before we go ahead and create our project in CEO, we want to plan out our project conceptually. So this involves coming up with the objectives that we aim to achieve with our image interpretation project, as well as what end product we want to produce in order to achieve those objectives. Furthermore, we're going to identify what imagery we need in order to create that end product, and we're also going to formulate what's called a sampling design as well as a response design. So in this video, we're going to cover those different steps of planning out your image interpretation project. So the first order of business when planning out your image interpretation project is going to be defining the objectives that you hope to achieve with this project. What's the question that you're looking to answer? What's your region and time period of interest? Once you have those objectives, you can define the end product that you want to create. This can be a land cover map, like the one shown here, or a statistical analysis of the different land cover classes present in your study area. So at the end of this unit, you will create your own image interpretation project, and I'll show you an example project that I created using Collectors Online. So in this case, my objective was to quantify the different land cover classes in the country of Ghana for the year of 2022. And I knew that in order to accomplish that objective, I wanted to create an end product that was a land cover map. And this land cover map, I knew I wanted to generate with machine learning that was trained on data that I collected in Collectors Online. So once you have identified what your end product will be, you can then create your classification schema, which just means a list of your land cover classes as well as an explicit definition of each class, and this will help you when you collect your data. So you can also use an existing classification schema rather than creating your own. So in my case, I use the European Space Agency's World Cover land cover map, and I used their classification schema associated with that map. And this allows me to directly compare my product with theirs. Once you have your classification schema, think about what imagery you'll need in order to be able to discern between the different classes in your schema. So, for example, let's say we had a very specific classification schema that sought to map the different kinds of crops in your study area. You would need very high spatial resolution imagery in order to distinguish between those classes of interest. But a broader land cover classification schema, like the one shown here, doesn't require as high of a spatial resolution of imagery. And this is important to consider when you create your project at the end of this unit, because there's often a cost associated with high spatial resolution imagery. So for our purposes, when we're creating a project that uses free and open source imagery, we probably want to stick to broader classification schemas like the one shown here. And I should note that this classification schema, this is not the whole thing that's shown here, this is just some of the classes. Another thing to consider, especially if your image interpretation project will use a machine learning algorithm, is that each class that your machine learning algorithm will map should be included in your classification schema. And if your machine learning algorithm will not map a certain class, we can incorporate those other land cover classes into a single background class if they are 1, rare, and 2, not of interest in mapping. Another thing to consider when you're making a machine learning model is that all of the data that is provided to the model should be provided to the data collector, which in this case is you. So if you wanted to use Landsat imagery in your machine learning classifier, you would want to upload Landsat data to your Collectors Online project. So the next step in planning your image interpretation project is going to be formulating your sampling design, which refers to how you will geographically place your samples within your region of interest. And the word sample just refers to the location where you'll be interpreting the imagery and classifying it as a certain land cover type. And so the sampling design that you implement will of course depend on the end product that your project aims to create. So the first decision that you have to make when creating your sampling design is choosing whether or not to use clusters. So clusters, which is shown by the image on the left here, group your pixels into separate groups. And so this can reduce the costs associated with an image interpretation project because it allows you to procure imagery just for these sections of your region of interest rather than the area at large. It's also very helpful if you plan on going out into the field and collecting data. But the problem with a clustered sampling design is you're ignoring a portion of your region of interest, right? And thus it's referred to as a geographically imbalanced sampling design. So for our uses, since we're likely not going to be going out into the field to collect ground truth data and we're not going to be buying any imagery, it's better to pursue a non-clustered sampling design. So that brings us to our next decision, which is a stratified sampling approach. So strata just refer to groups of pixels that are both exhaustive and exclusive. And what I mean when I say that is that each pixel within your area of interest can be assigned to one and only one strata. So at the top of this figure on the right here, we can see a sampling approach in which strata is not used and we're just randomly distributing points within our region of interest. But at the bottom here, you can see that strata are used and we're randomly distributing points within each strata. So land cover is often used as a strata itself. So you can take a pre-existing land cover map, divide it into those land cover classes, and then randomly distribute points within each land cover class as identified by that pre-existing map. So earlier I showed the classification schema for ESA's world cover product. Not only did I borrow that classification schema for my interpretation project, but I also used that world cover map to conduct a stratified sampling approach. And this is really helpful when you're training a machine learning generated land cover map because it allows you to sample points from your rare land cover classes like mangrove forests. The next decision you want to make refers to allocation, which just means how you're going to distribute your samples within your clusters, within your strata, or within your region of interest if you plan on using neither cluster nor strata. And I should also mention that both clustering and stratification are mutually exclusive decisions, right? So we can use both, we can use either one, or we can use none. And so the different types of allocation are uniform allocation, where we're distributing points within our strata or clusters in a uniform grid, and random allocation, where we're randomly distributing those points. Finally, you're going to want to determine your sample size, which is how many points you will collect within your region of interest. So if your end product will be a machine learning generated land cover map, your sample size is going to depend on both the number of spectral bands used in your classifier times the number of classes in your classification schema. So the literature recommends that you collect at least 10 times this product, but other research indicates that you should collect as high as 30 times the product of spectral bands and your number of land cover classes. And the reason you want to collect that many sample points is you want to capture the intra-class variance of each class in each band that you use in your classifier. And what this means is you want to capture how the spectral response might change for each land cover class depending on the time of day the image was taken as well as the time of year. For the purposes of your project, we're probably going to want to stick to this lower estimate of 10 times the product of spectral bands and classes because it's important to remember that it takes at least 60 seconds to collect just one sample. So depending on the number of bands you plan to use as well as the number of classes, this sample size can get fairly large fairly quickly. But when you're conducting a image interpretation project with a large number of data collectors, you can split up how many samples are collected between the group and you can collect more samples. If your end product will be assessing the accuracy of an existing land cover map, there's a good guide to obtaining a sufficient sample size in order to do that, which will be linked in the course materials here as well. Your final step when planning out your project is going to be developing what's called a response design, which refers to the protocol that you will undergo when interpreting the imagery and classifying your assessment unit. So your assessment unit refers to the area that you'll be classifying as one land cover class at each sampling location. So first you have to decide whether you want to use an aerial-based assessment unit or a pixel-based assessment unit. So a pixel-based assessment unit refers to the fact that you will interpret the land cover only at the pixel the very specific pixel at which your sample is located. Whereas an aerial-based assessment unit is an area of a certain size that's centered on the pixel that your sample is located at. So you need to consult your classification schema when making this decision of a pixel-based or an aerial-based assessment unit, because certain classification schema require an aerial assessment unit. For example, the classification schema that I used had a definition of forest where at least 10% of the assessment unit had to be covered in trees in order for the assessment unit to be classified as forest. So in my case, I pursued an aerial-based assessment unit. And if you do choose an aerial-based assessment unit, you need to determine the size of that unit. So in my case, since I sought to train a machine learning model, I made my assessment unit size 10 meters by 10 meters in order to match the resolution of the coarsest input data to my machine learning model, which in my case was Sentinel-1 and Sentinel-2 imagery. Your next step when creating your response design is going to be coming up with questions and responses for each assessment unit. So if your project sought to examine the land cover change of a certain region of interest between 2015 and 2020, you might have two questions, the first being what's the land cover type in 2015, and the second being what is the land cover type in 2020. And the responses to both of those questions would just be the different land cover classes that are present in your classification schema. Finally, a large component of your response design is going to be coming up with a set of rules for you to adhere to when you're collecting this data and classifying each assessment unit. So if your end product is going to be a machine learning generated map, you want to feed only assessment units that are pure pixels. That is, the whole assessment unit is one land cover class. So you might come up with a rule for yourself that says that if greater than 90% of the assessment unit is a single land cover class, I'll interpret the entire assessment unit as that class. And if there are mixed pixels, like in this image shown in the bottom right, let's say that these squares with these hatch marks represent one land cover class and these white squares represent another land cover class. If I encountered an assessment unit like this, I might just flag the plot and discard it from the data collection process. So you want to come up with specific rules for yourself to adhere to later on when you're collecting data. And that way the data collection process is consistent with itself. So that's it for this video. Now we know more about sampling design and response design and planning our image interpretation project as a whole. So later on when we create our image interpretation projects, we're going to plan this whole project out on paper, and then we'll be able to implement each step of the project planning in Collect Earth Online. So these are the references that I used when creating this presentation, and I highly recommend, as I said earlier, this Stemmen paper from 2009, which provides a lot of great context and definitions for the terms I discussed in this video. So that's all for this video, and thank you for listening. Collect Earth Online has received financial support from NASA, the U.S. Agency for International Development, or USAID, the Food and Agriculture Organization of the United Nations, or FAO, the U.S. Forest Service, Silva Carbon, Google, and the Spatial Informatics Group. It was co-developed as an online tool housed within the Open Forest Initiative of FAO. Collect Earth Online was initially developed by Servier and is now supported by a broad base of partners. And it was inspired by Collect Earth, a desktop software developed by FAO. The development team of CEO includes Arthur Lewes, Jordan Combs, Matt Spencer, Richard Shepard, Oliver Baldwin Edwards, Sif Beery, Roberto Fontanarosa, Francisco Delgado, Githika Tondapu, Billy Ashmal, Nishanta Kanal, John Dilger, Karen Dyson, Karis Tennyson, Cal Markert, Africa Flores, Emil Sherrington, and Eric Anderson. The Collect Earth Online curriculum was organized by Servier's Science Coordination Office, with individual models created by NASA, USAID, NASA's Earth Observatory, the Spatial Informatics Group, and Servier's Science Coordination Office. These individual modules were created by Crystal Wespestad of Spatial Informatics Group, Holly Rybeek and Robert Simon of NASA Earth Observatory, Billy Ashmal, and myself, Mickey Maganini, of Servier's Science Coordination Office. Review of the material was conducted by Sevier's Science Coordination Office, including Kelsey Herndon, Emil Sherrington, Billy Ashmall, Deanna West, Katie Walker, Lauren Carey, Jacob Abramowitz, Jake Ramthen, Natalia Bermudez, Stephanie Melik, Emily Adams, Stephanie Jimenez, Vanessa Martin, Alex Goberna, Francisca Delgado, Biplab Bhandari, and Amanda Markert. Crucial insight regarding the development of the curricular materials was provided by Claudia Paris and Andrea Puzzi-Nicolau. Review of the material was also conducted by Bart Kroll and Laura Cray of ITC, the Faculty of Geo-information Science and Earth Observation at the University of Twente. The course and unit banner images used in the course were created by Gianluca Ambrosi of ITC.